Hello all, welcome to the new lecture of the chapter Congruences. In this lecture, we are continuing the problems using the congruence relations. Here we discuss about the towers of powers modulo m. So the first problem is find the last digit in the decimal value of 1999 raised to 1998 whole raised to 1999. So here the power is of the form a raised to b raised to c. So we know that a raised to b raised to c can be treated as a raised to in bracket b raised to c. So here the problem is to find the last digit in the decimal expansion of this power. And from the number itself, it is very clear that this is a very large number. And the last digit in this number will be the digit congruent to the number which is congruent to n modulo n. So we denote this number of which we have to find the decimal, the last digit by capital N. So let n denote the number, the given number. So the last digit of n, therefore the last digit of in n equals the least residue is equals the least residue of n modulo 10. Last digit is obtained by taking the congruence modulo when divided by 10. Okay. So the base number is 1990 raised to 1990. Sorry, this is not 1999. The question is 1990 raised 1997. So the base is 1997, and we know that this is congruent to 7 modulo 10. So 1997 is congruent to 7 modulo 10. So any power of the last digit may be instead of taking 1997, we have to consider 7, the power of 7. Now we will check the various powers of 7. Now the powers of 7 under modulo 10 are 7 raised to 1 is actually congruent to 7 modulo 10, and 7 square. 7 square is congruent to 7 square is 49. So it is congruent to 9 modulo 10. Then 7 cube. 7 cube is 9 into again 7. 9 into 7 number will be 63. The 3 will be the last digit. So congruent to 3 modulo 10. Then 7 raised to 4. It is 3 into 7. So it is congruent to the last digit will be 1. 1 modulo 10. Now again since we obtained 1, 7 raised to 4, the power of 4. When we take the power as 4, it is congruent to 1. Now we take the another higher powers 5. 7 raised to 5, we can see that this all powers will repeat. So 7 raised to 5 is again congruent to 7 modulo 10, and 7 raised to 6 is 7 square. 7 square is congruent to 9. So this will repeat again. So we can see that 7 raised to 1 is 7 under modulo 10. 7 raised to 1 is congruent to 7. 7 square is congruent to 9. 7 cube is congruent to 3. And 7 raised to 4 congruent to 1. So these are this, if we consider the power 7 raised to a, these powers are congruent to either 1, 3, 7 or 9 according to the power. A is where it is congruent to um, is congruent to uh, congruent to 0, 1, 2, 3 or when A is divided by 4. The least residues when obtained when A divided by 4. Because only the existing powers are 1, 2, 3 and 4 and from 5 onwards it again repeats. Okay, so the powers are actually the least residues to which A is congruent under modulo 4 least residues. So we can say that 7 raised to A is congruent to 0. Sorry, not 0. 7 raised to A powers we obtained are 1, 3, and 7 and 9. So it is congruent to 1 under modulo 10. 1 modulo 10 if എപ്പോഴാണ് A എന്നുള്ള നമ്പർ if A is congruent to 1 വരുന്നത് എപ്പോഴാണ് it's a multiple of 4 ആണെങ്കിൽ അല്ലേ when 7 raised to 4 is 1 now similarly we can say that 7 raised to 8 is congruent to 1 modulo 4 7 raised to 12 is congruent to 1 modulo uh, 10 like that. So if A is congruent to 0 modulo 4, that means A is a multiple of 4. Now it is is congruent to 3 modulo 10 if when 3 എപ്പോഴാണ് വരുന്നത് if sorry 3 അല്ല A congruent to 1 ആകുമ്പോൾ it is 7. We can write like that. So this is congruent to 7 modulo 10 if A congruent to 1 modulo 4. Now if A congruent to 2 modulo 4, it is 9, 7 raised to A is congruent to 9 modulo 10. Then if A is congruent to the last one 3 modulo 4, then it is 3 modulo 10. 7 raised to A is congruent to 3 modulo 10 if A is congruent to 3 modulo 8. So these are the digits. Now we have to, but instead of A here we have, here A is actually what 1998 raised to 1999 which is again A power. So for this we have to consider first the base 1998. We have to find the to which number it is. We have to find the least residue of this number when divided by 4, isn't it? Then only we can take the power of 7 as A. So we can see that 1998. If it is 96, it is congruent to 0 modulo 4. So therefore this is congruent to 2 mod 4. Okay. So this is congruent to 2 mod 4. But the number is actually 1998 raised to 1999. So any number 1998 raised to n is congruent to some 2 raised to n modulo 4, isn't it? Because by the last theorem we proved in the last lecture, that is lecture number 4. So 1998 raised to n congruent to 2 raised to n modulo 4. Now we have to look at the nature of 2 raised to n. Suppose if n is the power is greater than or equal to 2, then 2 raised to, that means if n is at least 2, then it is 2 square which is a multiple of 4 which is congruent to 0 mod 4, and if it is 2 raised to 3 it is again congruent to, it is a multiple of 4. Or if n is greater than or equal to 2, n is a number which is greater than or equal to 2, then all such powers will contain 4 as a factor. So this will be congruent to 0 modulo 4. So if n is greater than 2, we have 1998 raised to n congruent to 2 raised to n modulo 4, and 2 raised to n modulo 4 is congruent to 0 modulo 4. So in total 1998 raised to n is congruent to 0 modulo 4. 1998 raised to n is congruent to 0 modulo 4 if n greater than or equal to 2. And now our power is actually the power in the problem of 1998 is 1999. So obviously the power 19 instead of n, here we have 1999, which is obviously greater than 2. So we have 1998 raised to the power 1999 is congruent to 0 modulo 4. That is, this is our A. That is, we have A is congruent to 0 modulo 4. Then by this result, let this be number 1. Therefore, by the result 1, by the result 1, 7 raised to 1998 raised to 1999 is congruent to, if A is congruent to 0 modulo 4, 7 raised to A is congruent to 1 modulo 10. So this will be congruent to 1 modulo 10. 1 modulo 10. So this will be that means 1997 raised to 1998 raised to 1999 is congruent to 1 modulo 10. So the last digit in the decimal expansion of this value is 1. Hence the proof. Now we move to another problem. Problem number 2. Show that 11 into 14 raised to n plus 1 is a composite integer. A composite integer, we know that it has a power, sorry, it has a factor other than 1 and that number itself. It has a divisor. So we need to prove that if n is, there are two cases whether n is even number or odd number. So in both cases we have to prove that this contains a prime factor. This has a prime factor, or there is a divisor, there is a prime number which divides this number. Let n is equal to this number. Let capital N equal to 11 into 14 raised to n plus 1. We have to show that, we shall show that there is a prime p such that p divides n for some p. So we consider it as a two cases. Case 1, n is even. We consider the prime 3. If we consider 3, we can see that 14 is congruent to, actually 15 is a multiple of 3. So 14 congruent to minus 1 modulo 3. So 14 raised to n is congruent to minus 1 raised to n modulo 3. Since n is even number, we have 14 raised to n congruent to 1 modulo 3. Now 11 also, 11 congruent to what? 9 is a multiple of 3. So 11 congruent to 2 modulo 3. So n is equal to 11 into 14 raised to n plus 1. So this is congruent to, or before doing this, combining this, multiplying these two congruences. By theorem, we know that we can multiply the two congruences of the same modulus. So 11 into 14 raised to n is congruent to 2 modulo 3. Now we can, one more thing we can write is 1 congruent to 1 modulo 3. So these are two congruences. Now we can add these two congruences, which is the number n. So n is congruent to 2 into 1 plus 1 modulo 3. Now this is 2 plus 1, it is 3. So this is congruent to, n is congruent to 0 modulo 3. That means by the definition of congruences, we have 3 divides n, which implies n is a composite number. That is, if n small n is even, then capital N is a composite number, since 3 is a prime number which divides n. Now we consider the case 2. N is odd. So if n is odd, we have 14 raised to n congruent to sorry, instead of this 3, we can try with the 5. So if n is odd, we know that 14 is congruent to minus 1 modulo 5. So 14 raised to n is congruent to minus 1 raised to n modulo 5. But since n is odd, it is congruent to minus 1 modulo 5. Now 11. 11 is congruent to actually 10 is a multiple of 5. So 11 congruent to 1 modulo 5. So 11 into 14 raised to n is congruent to minus 1 modulo 5. And 1 congruent to 1 modulo 5. Now adding these two, we have 11 into 14 raised to n is congruent to minus 1 modulo 5. Sorry. Adding these two, we have 11 into 14 raised to n plus 1 is congruent to minus 1 plus 1 modulo 5. That is, capital N is congruent to 0 modulo 5, which implies 5 divides n, which implies n is a composite number. 5 is a divisor of n. So in both cases, we have seen that n is a composite number. Now we take problem number 3. Find the remainder when n square plus n plus 41 whole square is divided by 12. So we need to find a remainder when this factor square is divided by 12. We know that the product of 4 consecutive integers is divisible by 12. First notice that the product of 4 consecutive integers is divisible by 12. That is If we consider n for the integer, we have n minus 1 into n plus 1 into n plus 2 will be the four consecutive integers. This is congruent to 0 modulo 12. And we have 41. 41 is congruent to what? 41 is congruent to, it is 36 is the power of 12, sorry, multiple of 12. So 36 plus 5, right? So 5 modulo 12. So 41 is congruent to 5 modulo 12. So keeping in this in mind, we have to consider n square plus n plus 41. So n square plus n plus 41 is congruent to n square plus n plus 5 modulo 12. So we have n square plus n plus 41 whole square is congruent to n square plus n plus 5 whole square modulo 12. Now expand this power. So it is n raised to 4 plus 2n cube plus or it is of the form a plus b plus c whole square. So it is a square n raised to 4 b square n square, then 2ab term, that is 2n cube plus 10 2 into n square into 5, that is 10n square, plus 2 into 5 into n, that is 10n, plus c square, that is 25 modulo 12. So again this is congruent to n raised to 4. Now adding the like terms to n cube plus 11n square plus 10n plus 25 is there. So this plus 25. Instead of 25 we can write it as 1 modulo 12. Since 25 is congruent to 1 modulo 12. So this is, and from these numbers we can take n outside. So n into no, instead of before taking n we can rewrite 11n square and 10n into some lower numbers least in terms of least squares. So this is n raised to 4 plus 2n cube. Since this number is big 11, so 11 is congruent to minus 1. 1 modulo 11 congruent to, we have 11 congruent to minus 1 modulo 12, and then we consider 10 is congruent to minus 2 modulo 12. So instead of 11 and 10 we can take minus 1 and minus 2 respectively. So minus 2n modulo 12, then plus 1 modulo 12. Now take n outside. So n into n cube plus 2n square minus of n plus 2 plus 1 modulo 12. So this is n into, here n square is common, n plus 2 minus of n plus 2 plus 1 modulo 12. So this is again congruent to what? N into n plus 2 into n square minus 1 plus 1 modulo 12. So this is congruent to n square minus 1, we can write as n minus 1 into n plus 1. So n minus 1 into n plus 1 into n plus 2 arranging in ascending order plus 1 modulo 12. We already know that this number is divisible by 12. So this is congruent to 1 modulo 12. So n square plus n plus 41 the whole square is congruent to 1 modulo 12. This is therefore the remainder obtained while dividing by 12 is 1. Now in the lecture of Fermat numbers, we have already proved that the fifth Fermat number is not a prime because it is divisible by 641. Okay, that is the fifth Fermat number F5 denoted by F5 is 2 raised to 5 plus 1. We have already proved that this is not a prime number as it is divisible by 641. That we have already shown. Now we try to give an alternate proof using congruence relations. So the problem is, this is actually our fourth problem. Problem is show that the Fermat number F5, fifth Fermat number is divisible by 641. First we notice that 641 is congruent to 1 modulo 641. Sorry, minus 640 is congruent to minus 1 modulo 641. So now 640, but we have to get what? 2 raised to 5 plus 1 modulo 641. So we have to reduce 640 in terms of 2 in the power of 2. So for that we write 640 as a power of 2. 640 is 320. Again this is 160. This is 80. This is 40. Then 40 when divided by 2 is 20. 20 divided by 2. This is 5. So 3 plus 4, 7. So 640 we have 2 raised to 7 into 5. So we have the result that 2 raised to 7 into 5 is congruent to what? Minus 1 modulo 641. But we have to make the power up to 2 raised to 5 means 2 raised to 32. So we have only 2 raised to 7. So we can take the fourth power of this equation. Let this be equation number 1. This is equation number 2. So taking the fourth power, we have 2 raised to 7 into 5 raised to 4 is congruent to minus 1 raised to 4 modulo 641. So 2 raised to 7 raised to 4 is 2 raised to 28 into 5 raised to 4 is congruent to again 1 modulo 641. Now we have to write 5 raised to 4. Instead of 5 raised to 4, we have to write number which is in less powers. So 5 raised to 4, we have 5 is congruent to on modulo 641. 5 square is 25 modulo 641, and we have 5 raised to 25 into 25 is 625. So 5 raised to 4 is congruent to 625. Then up to 41 it is 25, 16, I think. So it is congruent to minus 16 modulo 641. Okay. So we have 5 raised to 4 is congruent to minus 16 modulo 641, and we know that 16 is congruent. 16 means it is minus 2 raised to 4. So instead of 5 raised to 4, we can use 641. Instead of this, we can use what, minus 2 raised to 4. So applying that in the equation, in this equation, that is equation number 3. Therefore, equation number 3 implies 2 raised to 28 into 5 raised to 4 is congruent to minus 2 raised to 28 into minus 2 raised to 4 modulo 641. That is congruent to okay. So, and this is congruent to what, from equation 3, this is congruent to 1 modulo 641. So this is congruent to actually 2 raised to minus 2 raised to 4 is congruent to, not minus 2 raised to 4, minus, so minus minus into 2 raised to 4. Negative of minus 2 negative of 2 raised to 4. So not like that. So this is minus 2 raised to 28 plus 4 is 32. Is congruent to 1 modulo 641. Or we can write this as 2 raised to 32 is congruent to minus 1 modulo 641. Or we can have 2 raised to 32 plus 1 is congruent to 0 modulo 641. That is 641 divides 2 raised to 32 plus 1. That is 2 raised to 32 plus 1 is 2 raised to 5 plus 1. That is F5, the Fermat's fifth prime. That is 641 divides F5. So this is an alternative proof for showing this, for proving this problem, which is we have already proved in the section with Fermat numbers. So the most suitable one we can use. Next we move to another result. We trying to prove another result for congruences which is more applicable. We know that cancellation laws hold in laws under multiplication. The cancellation property, cancellation laws of multiplication holds. That is, if AC is equal to BC, then with C not equal to 0, then we can cancel that common factor C and we have A equal to B. Now we are trying to we are searching for a relation, if it is possible, if there are any congruence relation similar to this we are trying to prove. That is, if AC is congruent to BC modulo M such that C not equal to 0, then is it possible is it possible to cancel C and write A congruent to B modulo M? The answer is no, it is not always possible, because we have an counter example. This is not always possible to cancel the common factor in congruences, because we have one example. Consider the congruence. 24 is congruent to 12 modulo 6. 12 modulo 6. Therefore, 24 we can write it as 3 into 8 is congruent to 3 into 4 modulo 6. So 3 is a common factor in both the numbers, but we can see that 8 is not congruent to 4 under modulo 6. 8 is not congruent to 4. So the relation AC congruent to BC modulo M will never always imply that A congruent to B modulo M. So, but this is true in some, if we imply some certain conditions or in certain some circumstances, this is true. But in certain cases, this is true. The conditions are explained in the next theorem. So we move to the next theorem, which gives the cancellation rule for congruences of multiplication. That is, if AC is congruent to BC modulo M with the condition that GCD of C comma M GCD of C comma M equal to 1, that is the common factor is relatively prime to the modulus, then A is congruent to B modulo M. Okay. So if the GCD of the common factor and modulus is 1, then we can cancel the common factor. This is our theorem. Now we have to prove this. So before proving, we can check whether what happens in the above example. What had happened in the above example. Here you can see that AC is congruent, 24 is congruent to 12 modulo 6. But when we consider here C, the common factor C is 3 and M is 6, and we can see that GCD of 3 6 is equal to 3, not equal to 1. That means 3 and 6 are not relatively prime. So we cannot apply the theorem 4.6 here in this relation. So it is not congruent to 4 modulo 6. Now we need to prove this result. Given that AC is congruent to BC modulo M, then by the definition of congruences, we have M divides AC minus BC, or AC minus BC is equal to M divides AC minus BC, or that is M divides C into A minus B. So M divides C into A minus B. So now we have M divides C into A minus B, and GCD of C comma M equal to 1. Then we have already studied one Euclid's lemma, one lemma called Euclid's lemma, which states that if A divides BC and GCD of A comma B equal to 1, then A divides C. So this is the result, Euclid's lemma. So applying this here, we have M divides C into A minus B, and GCD of M comma C is equal to 1. Then by the lemma, Euclid's lemma, M divides A minus B, or in other words we can say that A is congruent to B modulo M, which is the required relation. So we can verify this theorem in an example. Using an example, consider the relation 78 is congruent to 48 modulo 5. 78 and 48. So 6 is a common factor. We can write this as 6 into 13 congruent to 6 into 8 modulo 5. Here C is equal to 6. 6 is a common factor. Now check the GCD of 6 with M, that is 6 and 5. GCD is, we know, it is 1. By the theorem, therefore by the above theorem, we can cancel 6 and write the congruence as 13 congruent to 8 modulo 5. Actually, we can use this cancellation property for reducing. Using this, we can reduce the higher congruences into some lower numbers, into some least congruences. Okay, so this is a very important property of congruences. Now we can generalize, we try to generalize this relation. We have seen that if AC is congruent to BC modulo M, then A congruent to B modulo M only if GCD of C comma M equal to 1. But suppose if GCD of C comma M not equal to M, let it be some number D. In this case, this is GCD of 3 comma 6 is equal to 3. So we have seen that this is not congruent to, it is not congruent to 4 modulo 6. But we can see that 8 must be congruent to 4 modulo M by D. So GCD of 3 comma 6 equal to 3, let it be D. So we can see that this is modulo, that is 8 is congruent to 4 modulo 2. This is true, isn't it? 8 minus 4 is 4, 4 is divisible by 2. So this relation is true. So even though A not congruent to B modulo M, we can see that here the result is A congruent to B modulo M by D, isn't it? So using this relation can be this can be generalized as a result. So generalization. Generalization of theorem 4.6. That is theorem 4.7. If it states that if AC is congruent to BC modulo M and GCD of C comma M equal to D, then A is congruent to B modulo M by D. So this is the generalized result. Now we move to the proof. Suppose AC congruent to, or given that AC is congruent to BC modulo M and GCD of C comma M equal to D. Then by this relation we have M divides AC minus BC, or AC minus BC is equal to M into some K, or C into A minus B is equal to M into K. Now divide throughout by D. Divide this equation by D. Then we have C by D into A minus B is congruent to M by D into K. So and we know one more thing, we know that So or we know we have GCD of C by D comma M by D is equal to 1. Since GCD of C comma M equal to D, then we have the result using this result, that is if GCD of A comma B equal to D, then GCD of A by D comma B by D equal to 1. The property of the GCD of two numbers, positive integers. So GCD of C by D, M by D equal to 1. So in this equation, let it be equation number 1. So equation number 1, equation 1 we can write in some other way, that is C by D into A minus B is equal to M by D into K, or this implies M by D divides C by D into A minus B. And we know by the properties of GCD that GCD of C by D comma M by D is equal to 1. Therefore again by Euclid's lemma that we have already used in the theorem 4.6. By Euclid's lemma we have M by D divides A minus B, that is A minus B is congruent to 0 modulo M by D, or A is congruent to B modulo M by D. So hence the generalization. So if AC congruent to BC modulo M, then A is congruent to B modulo M by D, where D is the GCD of C comma M. And if D is equal to 1, then we have the theorem 4.6. If D is equal to 1, then it is congruent, A is congruent to B modulo M. So we will get the result when D is equal to 1. So this is the generalized theorem. So for example, consider 8 into 37 is congruent to 8 into 7 modulo 12. We can verify this. We know that 8 into 7 is 56, 8 into 37. 37 into 3, that is 296, and 296 minus 56 is 240, which is divisible by 12. So this result is true. This congruence holds. And 8 is a common factor, and we can see that GCD of 8 comma 12 is 4. So we have 37 congruent to 8, we can cancel 7 under modulo 12 by 4, or 37 congruent to 7 modulo 3, which is true since 30 is divisible by 3. So we can reduce the congruences. Now we will discuss another important theorem which gives the congruences of two numbers with a different moduli can be combined into a single congruence. So this is a theorem for combining congruences with a different moduli into a single congruence. If statement is like this: if A is congruent to B modulo M1 and A congruent to B modulo M2, etc., A is congruent to B modulo some Mk, then A is congruent to B modulo GCD of M1, M2, etc., Mk. So, in this way, we can combine the modulus of the congruences with the different moduli into a single modulus. Let's look at the proof. Given that A is congruent to B modulo M1, if since A congruent to B modulo M1, we have M1 divides A minus B by the definition. Similarly, we have A is congruent to B modulo M2 implies M2 divides A minus B, etc. A congruent to B modulo MK implies mk divides a minus b. So m1, m2, etc. mk divides a minus b. That means a minus b has m1, m2, etc. mk are divisors of a minus b. Then by the property of divisibility property, we have their LCM also divides. So the LCM also divides a minus b by the property of LCMs. That is, we have one corollary. By the corollary 3.12, that is, if m1, m2, etc. mk are integers such that mi divides a for 1 less than or equal to I less than or equal to k, then their LCM m1, m2, etc. mk also divides a. Okay, using this result, we have m1 divides, m1 is a divisor of a minus b, m2 is a divisor, etc. mk is a divisor. Therefore, combining all that, we can say that the LCM of m1, m2, etc. mk divides a minus b. Or converting into the definition of congruences, we have a minus b is congruent to 0 modulo LCM of M1, M2, etc. MK. This LCM of this one, or A is congruent to B modulo LCM of M1, M2, etc. MK. Yes, we can convert all these integrals with different congruences with different moduli into a congruence with a single modulus. So, our section 4.1 of chapter congruences is over. So there are so many problems in the exercise. Please do the problems and copy that into your notebook, and if you have any doubts that we can discuss. Okay, so try to do so many problems as possible. Okay, let's stop here. Thank you all.